Hello and welcome to the video. I have had this Telensa unit for a while. I was initially like, well, do I have to do another lamppost video? The other one was really conclusive. I tore it down. I disassembled the 8051 assembly language. I shown it in operation. I reprogrammed it so the 64-byte payload would keep repeating, so I could show that on camera. I shown the voltages in various parts of the board, its separation. But lo and behold, the man, the mystery that is Mark Steele, is back on social media again, talking about this unit. So today what we're going to do is we're going to explore the Telensa unit. We're going to, first of all, look at the various MCUs and chipsets that are on this device. We're going to look at how this 3,500 watt relay is actually just switching between. So that is 240 volts in. That's your 240 volts out to your light. You could say that to that man till you're blue in the face. He will not believe you. Well, let's say he won't agree with you because ultimately he knows that this is just a switch. So, yeah, and we've also got two death-ray capacitor packages as well. So we got that. Right then, so what we're going to do is going to get the microscope on this. And we are going to examine this. Right, let's do it. Right, so the first chip we're going to look at is the brains of the operation. This is the ARM STM32L100. So we're just going to grab some information on that. Oh, STM32L100. This is the value line of ST components. Oh, the STM32L1 series now hosts an entry-level line of the 30. Oh no, what is this about, Mr. Steele? Yep, this is our guy here, the RB series, 128K. 10K. Oh, yes, let's look at that data sheet, shall we? Like, oh wow, okay, like, yeah, what is this gonna do? This is like, yeah, I don't know. it's just a very, very basic microcontroller. Yeah. With ARM architecture. Oh look, it can hold up to 2 kilobytes of true EEPROM. Yeah, 128 kilobytes of flash memory. Wow, this is like, yeah, wow. So this is the brains of the operation on the board. As you can see, it's very, very low spec. Right, so the next component we're going to look at on the board is the Skytrack Venus 815 series of GPS receiver chip. Yeah, so, you know, this is just a GPS receiver. It's it's not really. I shouldn't even be having to talk about this, but you've got to cover all your bases, right? And yeah, and just to reiterate, receiver. This isn't doing any crazy kind of transmission. This is just basically receiving an EMEA string from 2 different satellites, minimum, ideally 3, 4, 5 satellites, and it just pinpoints its location. This will be for real-time reporting to the control center controlling these lights. So if there's a problem, they have a pin within a few meter radius idea of what light has failed within that kind of grid of lights on the streets. There's nothing really remarkable about this. I say I shouldn't even really need to be talking about it, but I'll talk about it and I'll scroll through as well. So, if anyone wants to go off and research any of this, you can just pause the video or play it really slow. And, yeah. Right, so the next component we're going to be looking at is the RF MCU that's in here. This is the guy that apparently would be executing the death ray or the whatever. I don't care, I don't really want to know, but this is the guy that's going to be doing all the frying and cooking of people, as Mark Steele claims. Okay, this is the Silicon Labs 4463 series of chips. Effectively, in the WiMAC unit I previously tore down and debunked, this is 4 generations on, because it was the SI1000, the previous chipsets in the WiMAC unit. This is the SI4000 series. I say 4 generations on. So we're just going to have a quick look at the spec of this. Cool. Yeah. So this is obviously a garage door opener. And if we come down to the spec, yep, it's all there. We know what it is. Okay. Yep. Frequency shift keying. Exactly the same. I say it's exactly the same as the SI1000. It's just 4 generations on this one. So it should be 4 times the kill grid, right? So if we come down to applications. Remote keyless entry. Aftermarket car alarms. Remote control IR replacement extension. Satellite set-top boxes, i.e. the satellite set-top box, it would be the remote control for that. Wireless weather stations, home security and automation. So this possibly will be from sensor to your main control box, or you'll have a key fob to disarm the alarm maybe. And the best one here is garage and gate door openers. I've actually seen this used in hospital beds where you get the remote. This very same 4000 series chipset is used in hospital beds, so the patient can press the remote and the bed goes up and down. So yeah, that's it's basically a switch, and we know it's a switch because it's in a bloody light, and it's in the light to switch the light. So okay, so basic block diagram, very very similar to the SI1000. Yeah, there's not much really to say about this. Yeah. So again, it's 805 on assembly. Yeah. Yep. Yeah, so basically it's a switch to switch things on and off, as you can see. Remote keyless entry, aftermarket car alarms, garage and gate door openers. Come on, Mark. Come on, stop lying to these people. Stop doing this. Stop causing these people distress, man. It's not a death ray. It's not some space age technology that's been hidden from us by governments and now is being rolled out. I've got the physical article here. Anyway, let's move on to some other components, shall we? Right, apologise about the shaky microscope. It's an overhead microscope and I've had to put it really high, and it's on a flexible arm, so if I just like move the table slightly, it goes nuts. Yeah, let's give you a demonstration of that. Right, so what you can see here, this is just below the relay. So this is the two contacts within the relay. This one and this one. And that's obviously driven by a low power current, which is over there. Or should I say switched, if that's the right term. So what we can see here, we have live in. This is a fuse as well. Comes in to that contact of the relay. Then we have that contact of the relay there. Goes through a second fuse. Goes to live out. So that relay is not responsible for anything else on the board other than the power coming in and the power going out. So power in, clicks through there, comes round, and that is live out. So there is no way that can interact with anything else on the board. That is the entire live circuit that relay switch is. So 3,500 watts is irrelevant. Absolutely irrelevant. Live in goes into one of the contacts of the relay. The relay is fired by a low current that's given to the relay by the MCU, and then what happens then is that those two contacts are connected, and we come through this fuse, and that goes to your light and switches your light on. This whole entire controller unit, its main purpose is to switch that live in to that live out. That's it. There is no other reason. And to argue the toss, you would have to be an idiot, because look at the traces. It's simple as that. That goes to that contact. So that live comes in from our 240 volt supply, goes down to that contact. That contact gets switched, and again straight through to live out. Down there. That's it. Very, very simple. So 3,500 watt relay is bullshit, isn't it? It's literally a switch. It's effectively the product of everything that goes on in this board, from the RFMCU, the microcontroller unit, the GPS. Ultimately, all of that culminates in switching between those two contacts. That's it. Right, so looking at here, this is the back of the Death Ray capacitors. Those are 450 volt bad boys. Cool. Let me get that so it's not shiny. Right. So these are the pins for them. Straight off the bat, we can notice here, this goes off into a bridge rectifier. Basically, this is a switching power supply. So these will go in. I mean, this is the same thing as the YMAC unit, really, apart from this has got two capacitors as well. These caps will be in parallel, probably. And we can see here on the negative part of the switching MOSFET, it goes off into ground, which is there. So these will be tied in. The two negatives will be tied in. And that obviously, our switching power supply just taps into that leg there, and that goes off to our power in, or our 240 volt in. So I'm just going to get this on a 240 volt in pad. So obviously I've got the two probes there. Right, one on the pad in, Yeah. Oh, sorry, it's conformal coating. Right, so that's voltage in. See? Alright, yeah, obviously there's going to be no continuity there because it's through a capacitor. It'll be the same here. Right, so they're both tied in together. Let's just have a look. So that's that. There's our bridge rectifier. Conformal coating again. Yep. And same up here. This is our to ground. Yep, and that should be to ground as well. Excellent. Right, so these are just two smoothing capacitors going across the positive and negative rail. It's as simple as that. Now I'm just going to see if I can, within the shot, get over to the... I can. Oh, that's excellent. Right, so we've got our low voltage side. Now, you can see the separation between the high voltage and the low voltage. And we've got a bridge rectifier there, which goes through. Cool, okay. So just there on the top, well, the top of the screen, that will be one of the negative rails. I'm just going to see and get on that rail. Might just have to scratch a bit of that conformal coating off. Cool, get on that rail. I'm just going to see if we can. Yep, no continuity there. No continuity there. No continuity there. No continuity there either. Right. Cool. Yep. Excellent. So as you can see, they're not tied in to any of these rails. So scratch a bit. From coating off at all. Not tied in anywhere. The reason being they're going through this bridge rectifier, they have no direct input to our chipsets here. This is our GPS chipset. And just there, you can see where the shielding goes, is our RF chipset. There is no way of it being tied in outside of this bridge rectifier, but this is just passing power through. There is no way of that power ever getting to the antenna. And it's the same on the other side of the board. You know, you can see all the separation there. It's physically impossible. It is physically impossible that through this switching power, basically it's with the caps on the other side, and this, it makes up a switching power supply. We've got the bridge rectifier, we've got the switching MOSFETs, underneath we've got our smoothing capacitors to smooth the electrical charge out, and this is just basically taking all that power and then it goes to a rail for our MCUs, our positive rail. We're not tied in at all on our low voltage side, and this low voltage side is just like all the components that are on it are rated for 3.3 volts. So just here, for instance, we would expect to see a voltage regulator, but we're not. So everything that's done is done through this switching power supply, and it's obvious that these capacitors have to smooth the ripple from the main supply coming in. It's that simple. There is no way that the 450 volts especially is getting through that switching power supply into these MCUs. I mean, and these MCUs anyway, as I've shown you on the spec sheet for the, because it's going to be the Silicon Labs chip, the 4th generation Silicon Labs chip that's over there. If I get that into shot, we'll talk about it. That Silicon Labs chip there, that's the culprit, right? Because that's the one that's tied in to the antenna. So that's the guy that's going to be distributing the def ray, right? Well, no, it's not. It physically can't do it. I mean, look at this separation. Massive separation. Why is there massive separation? To stop high voltage current flowing into the low voltage side. Yeah, so as we've noted, duly noted, is this is our switching power supply. Basically, the voltage is regulated down, it's rectified down, and it just goes off into the board. And on the other side of the board, there's nothing really, some resistors, bits and pieces, there's an inductor. But yeah, that's how we get our voltage down. And there'll be little tiny voltage regulators, but those voltage regulators will just be taking, like 6 volts down. I mean, there's obviously they're in. Can you see it there? Hang on, where are you? Yeah. Yes, there's a little coil just there as well. That's part of the rectification. That's on obviously directly below our switching power supply, so that'll be involved in taking the voltage down as well. Yeah, it's as simple as that. There, I say we've shown that there's no connection, and how even like in an ideal world where conspiracy theories are true, there is no physical way that these packages are going to take that kind of voltage anyway, and there's no way it's going to end up somehow in an MCU that's rated 3.3 volts and has a very, very weak output, and the packets, for instance, like 64 kilobyte payloads. And even in the manual, the Silicon Labs manual, they specify that don't run it, more than once every 15 seconds. So that's 64 bytes of data every 15 seconds. I'm going to call bullshit on this. I may or may not do a video with this live. I do have the programmer for the... Get it in short. That little STM fella down there. I do have the programmer for that. So I might see if we can get on that and do some programming, or at least see if we can pull the ROM off it. I'm assuming because it's an STM chip as well, it's going to be a lot more locked down than the 805 assembly I encountered on the WiMAC unit, the previous teardown. I did one of these lamppost switches. But yeah, cool. So I'm going to call it today. If you want me to get a program on it, put in the comments whether I lose or have a win for the boys there and the girls, and let's not be sexist. Whether I have a win or not, I'll probably post that video as well of me just twiddling and trying to bit bang it. But yeah, cool. Well, thanks for watching the video, and I'll catch you in the next one.